On behalf of the Indian Academy of Sciences, I have great pleasure in welcoming you all to the 28th mid-year meeting of the Academy.
Let me start by thanking the academic for inviting me and allowing me to give this presentation. Today I'll talk about topological phases of quantum matter. As many of you may know, the 2016 Nobel Prize in Physics was awarded to Thouless, Haldane and Kosterlitz for theoretical discoveries of topological phase transitions and topological phases of matter. And although this was the first Nobel Prize to mention topological phases, I should say that this is not really the first Nobel for topological phases. In 1982, the Nobel Prize was awarded to von Klitzing for the discovery of quantized Hall effect. And now it is known that this is the first topological phase. The second one was awarded in 1998 to Laughlin, Stormer and Tsui for the discovery of a new form of quantum fluid with fractionally charged excitations. This was the fractional quantum Hall effect, which is also now known to be a topological phase. So let me start by saying, what do we mean by phases? All of you would have heard of solid, liquid and gas phases, but there are many more complicated phases can exist, and one can think of a phase as a collection of particles with some properties which distinguish them from others. Earlier, the phases were classified in terms of expectation values of what are called local order parameters and broken symmetries. For instance, ferromagnets broke rotational symmetry and had all its spins pointing in one direction. Now, in the last 10 years or so, there's been a paradigm shift in the way of classifying phases. Now one classifies phases based on topology. And just defining topology, it's a branch of mathematics that deals with quantities that are invariant under small continuous changes. You can change a winding slightly like this, but the winding number will not change. Topological invariance, such as winding numbers, genus of surfaces, etc., it depends on the system as a whole and cannot be determined locally. You can't look at a small piece of the surface and see whether you're on a sphere or on a donut. You have to look at the entire system. And changing the topological invariance, such as the genus of a surface, requires drastic measures such as punching a hole. So how does all this affect topological physics? The first, as I said, the first topological phase was discovered 30 years ago, which is the integer quantum Hall state. In the integer quantum Hall effect, which was what von Klitzing got his prize for, electrons were constrained to move in 2 dimensions in the presence of a magnetic field in the perpendicular direction. And experimentally, when they measured the Hall current, it showed quantized Hall plateaus. And essentially, the explanation at that time was given because all of the bulk states in the interior of the sample did not conduct. They had a gap, which means that they needed an energy to be excited. So they cannot carry current, and it's only states at the edge of the sample which could carry current. So this was the integer quantum Hall effect. Thouless, who got the Nobel Prize in 2016, and his collaborators understood that the quantum Hall state was an example of a topological phase. They realized that the wave functions actually get knotted by the magnetic field and form a phase which is distinct from all other phases, and that phase can change only when drastic changes are made, such as when a gap is closed or when the number of edge states decreases. You need to have some gapless edge states when you go from a topologically non-trivial state to a topologically trivial state. The current interest in topological insulators actually began in 2005 when it was realized that the knotting of the wave functions and the topologically quantized conductance can happen even in the absence of strong magnetic fields and low temperatures. There are materials in which it can happen intrinsically. All that is needed was strong spin-orbit coupling. And so materials with strong spin-orbit coupling can behave like a quantum Hall state. That is, they're insulating in the bulk, and they have edge states or surface states which carry the current. You can think of it like a block of wood covered by a metal, except that the entire thing is one material. It was not, these kinds of materials existed but couldn't be discovered earlier for many reasons, including the need for sophisticated experiments or instruments that could actually map local density of states and to know which states carry current. And theoretically, it required things like understanding of Berry phase, structures of mappings of Brillouin zone to the Hamiltonian, more information than was available at that time, which is just dispersions of materials. These phases, these materials were predicted theoretically and then experimentally observed, which is very unusual in condensed matter physics. These phases also have very unusual transport, because the transport, which is actually through quasi-particles which are emergent excitations inside the material, need not just be bosons or fermions. They can be what are called anyons and even non-abelian quasi-particles like Majorana zero modes. And what do I mean by this? Essentially, one knows that in quantum theory, the probability for a process is the square of the amplitude of its wave function. So what we need is that if they are indistinguishable particles, you don't know whether as in the timeline of the particle, whether the particles have gone like this or they have been exchanged. And you need to add the amplitudes or have some rule of, these are called world lines of these particles, quasi-particles. And quantum statistics actually reflects the topology of the world lines. Rules, it gives us rules for how we add the contribution from different classes. In 3 dimensions, it happens that you can only add them, which gives you bosons, or subtract them, which gives you fermions. But in 2 dimensions, you can add the phases with any paths, leading to anyon statistics. Technically, because removing a single point in 2D makes the space multiply connected. And it turns out that in many of the topological phases, in particular the fractional quantum Hall effect, quasi-particle excitations are anyons. Some topological phases also have non-abelian excitations, whose exchanges can give more than just a phase. These particles have an internal degree of freedom which includes what is called a topological degeneracy. It's topological because no local measurement can distinguish between the states. Degeneracy, of course, means that you have many states with the same energy. So when these particles, which have multi-component wave functions because you are in a degenerate space, get exchanged, they also get rotated within this space. So the quantum state can actually change under an exchange of identical particles. So since these rotations, since they can get rotated and rotations don't commute, these are called non-abelian. It depends on the order in which you do these things, whether you do one rotation first or the second rotation later. So one can also ask, why are people so excited about all these topological phases? One of the reasons that this has captured the imagination of people is because it may have applications to topological quantum computation. These non-abelian excitations imply that there is a robust degeneracy of the ground state, and exchange or braiding of these operators can move between these degenerate ground states, but it's actually, since it's a topological quantity, it's insensitive to details such as noise or interactions. So this could be useful in quantum computation, and this is one of the reasons for the current excitement in this field. There's been a second paradigm shift in condensed matter in recent times, and the other thing that people have now realized is that there is something called relativistic condensed matter physics. The standard wisdom was that electrons in solids are low energy particles and move at non-relativistic speeds and obey Schrödinger equation. But the recent realization is that in some cases, electrons in solids actually mathematically obey relativistic equations. Only the speed of light gets replaced by the speed of the electrons in the solid, which is the Fermi velocity. This was first seen in 1D physics in quantum wires or quantum Hall edge states, but now in 2D as well. The previous speaker spoke about graphene, which is made up of carbon atoms on a hexagonal lattice, and he talked about the Dirac nodes that you get, and at low energies around these Dirac nodes the dispersion is linear and the electrons obey massless Dirac equation. The only difference is that instead of in relativistic quantum mechanics you would have had them moving with the speed of light, now they move with the speed v is 10 to the 6 meters per second. And the spin is actually replaced by what is called pseudospin or the sublattice index over here. And in fact, for all I've told you now and what was considered true till just a few years ago was that the bulk of the material, to get a topological phase, the idea was that the bulk of the material should be gapless, should be insulating, that is, it should be gapped, and it's only the surface states which could be conducting or have topological phases. But in the last few years, one has also given rise to metallic phases which are topological, which is the wild semi-metal phase. How does this happen? This is not so easy to see, so I won't try to explain that. I will only say that there are also unusual technical features about the structure of the states of this wild semi-metal and the surface states, which are very different from usual metals and insulators. And this gives rise to interesting physical consequences. When magnetic field is applied in the same direction as an electric field in these materials, the resistance decreases with increasing magnetic field. This is not what happens for usual metals, negative magnetoresistance. Are there other physical consequences? Perhaps, and this is part of the research that I will also talk about. It's part of current research. I should say that I started my career in 1985 with topological field theories, which are now used as one of the tools to study topological phases. And what we did was we obtained a topological Ward identity, which showed that the coefficient of the non-abelian Chern, this is technical, I'm just mentioning it, of the non-abelian Chern-Simons term, which has to be quantized as an integer for topological reasons, gets renormalized only at one loop level by an integer, and there are no further corrections beyond that. The surprise was that perturbation theory actually seemed to know about topology. This work was carried forward much later and connected up with things like Jones polynomials, knots, etc. And in all these intermediate years, I didn't work much in exactly in topological phases. I basically worked a little bit on it, which are on anyons. I also worked on edge states of quantum Hall problems, Luttinger liquids, a little bit on graphene, etc. For main collaborator for many years was Deeptima and Sen, and there have been many others as well in these years. But I wanted to mention now at the end of my career, it again looks like I'm back to topological phases, which is what I started my career with. Now I'm part of the global effort to understand these topological phases theoretically. There are efforts now to classify them, efforts to find newer phases, efforts to see how they behave when they are juxtaposed with other materials, topological and non-topological, what happens when they are driven, that is, you put light on them, bulk edge correspondence, what happens when you include disorder, interactions, finite temperature, etc., how much of an effect is topological, and also, most importantly, efforts to understand how these excitations can lead to fault-tolerant quantum computation, which is kind of a goal in this field. I'll just mention my current collaborators. I have many PhD students who are working with me, postdoc, and I also collaborate a lot with my former students who are now faculty members in various institutes in the country. There are also a couple of faculty members from other parts of the world whom I'm collaborating with. So I'll now talk about a little bit, mention what is the work that I've been doing, try to explain it non-technically. So one of the things that we're working on is the edge structure of integer quantum Hall effect. As I said, the integer quantum Hall effect in the bulk is well understood without interactions and is known to have a conductance given by G is equal to nu E squared by H for nu fill Landau levels, if nu can be 1, 2, 3, etc. Naively, this means that at the edge also you should have new excitations. That's the bulk edge correspondence. There should be new massless edge, chiral edge states left-handed at one end, right-handed at the other end. But at the edges, it has been known that Coulomb interactions between the electrons can actually play a role, and depending on whether the potential at the edge, you can either have abrupt potentials or you can have smooth potentials at the edge, the background potentials. It depends, the number and position of the quantum Hall edge states can be changed. This is something which is called charge reconstruction and has been known. And essentially it happens because at the edges, they're massless, and as you make the edge smoother, the idea is that you want to, the electrons, this is the background positive potential, the electrons want to follow it as much as possible to lower the energy. So this is why you have something called charge reconstruction. The question we asked is, if there are multiple edge modes with the same spin, then is an exchange driven interaction possible? The simplest case here is to have nu is equal to 3, because they will have at least two modes with the same spin. For very sharp edges, the 3 modes are very close to each other, but as the edge is made smoother, they can move away from each other. And what you find is that at some point they are far enough away so that they can gain energy by having two like spins. Here you see that you have an up spin, a down spin, and an up spin. It becomes energetically favorable to have two like spins next to each other, even making up for the loss in energy by flipping the spins. So this is what happens. In the case that I have shown over here, the middle and the inner spins flip at the Fermi level. And so what happens is that if you at the edges, if you have a 0 up, these are the Landau level labels, 0 up, 0 down, 1 up, you find that when you make the edge smoother, it flips to 0 up, 1 down. The spin of these two have flipped. For other parameters, you can also make the spin of these two flip. The idea is that you want to have the two like spins next to each other, because that way it gains exchange energy. That is one of the things that we're working on. We've also been working on wild semimetals for a while now. Since it's known that when topological insulators are kept close to superconductors, new phenomena such as topological superconductor, new excitations within non-abelian statistics arise, we focused on what happens when wild semimetals are juxtaposed with a superconductor. We also found that experiments to detect exotic effects become more feasible when some of the parameters can be changed externally. We found that shining light on wild semimetals is an easy way to change some relevant parameters. So we focused on that as well. So I'm just mentioning some of the work that we've done recently. This was proximity-induced superconductivity in wild semimetals, where we wanted to see how much of the superconducting correlations survive inside this. And we found that even though it's a metallic, it does not survive very much. And we also looked at what happens when you have superconductor on both sides of a wild semimetal, and looked at the Josephson current in this. What we found is that due to a new scale in the wild semimetal, the Josephson current had some periodicities due to this, as a function of this new scale in the parameter, which is induced actually by time reversal breaking in this wild semimetal. The oscillations also changed the sign of the critical current. That is, we got 0 pi transitions. And we found that one could tune these 0 pi transitions by effective value of k0 by shining light on the wild semimetal. This actually makes the 0 pi transitions experimentally feasible. You can shine light and you can measure these things. We've also been working on other materials like silicene, which is similar to graphene, except that it has a buccal structure, and in general materials with larger spin orbit coupling than the graphene. In silicene, an external field can tune the band gap so that it can behave either as a normal insulator, a metal, or a topological insulator. And we've worked on various aspects of this, how to tune to Wally and spin polarized transport under appropriate magnetic fields and barriers. We've also studied effect of shining light on these materials to obtain new topological phases in the high frequency material. We're also trying to do this now at lower frequencies, and we find that we get other winding numbers which are involved. And finally, I also wanted to mention some work that we've been doing on Majorana modes, because the race to find Majorana modes, which are these non-abelian particles which are likely to be relevant in quantum computation, continues. And one of the questions is, although several candidates exist, one problem has been the unambiguous identification of a Majorana bound state as compared to other accidental zero energy bound states. And in this context, we have proposed a ring geometry. We've suggested that if you have an Aharonov-Bohm ring and measure currents and apply leads to it and measure currents as a function of this Aharonov-Bohm flux, then if you, whether you have a Majorana bound state or an accidental or an Andreev bound state, as this thing can easily be seen. Because if you have, we've found that if you have a Majorana bound state, then the currents at the two leads are anti-correlated. If this is the current through one lead, this is the current through the opposite lead. Whereas an accidental bound state, zero energy bound state, the current will always be the same. So this would be like a striking feature of finding these non-abelian bound states. So to conclude, I'm having fun working with topological phases and various cases and hope to continue.
Quantum computing?
At the moment, these non-abelian excitations have not yet been found. So it's very far from really being in a stage where you can use them to make quantum computers. But I think if they were found, and if they in the material in which they are found is sufficiently stable, it will actually be useful.